All right, we have another problem here where we have to figure out what type of hypothesis test to do as well as what type of error could have happened. So let's take a look. We got the core mathematics project. They have some field tests going on. They compare the performances of students taught using a traditional curriculum as well as this core plus mathematics project. And solve some algebra problems. They got the scores from 320 CPMP students and 273 in the math program. And then below here, we have the information from that number of students, average score, as well as the standard deviation. Now we're asked if there is evidence of a difference in performance between CPMP and traditional math programs. All right, so first of all, we're looking at evidence. So we definitely know we're doing a hypothesis test. We're looking to see if there is a difference in performances. So we're going to be comparing two things. We got two different populations here, CPMP and traditional. And we're looking at scores here. We're not looking at like percentages or anything. We're looking at scores, raw scores, 29, 38.4. These are averages. So we're going to be comparing averages from two different populations. If I'm comparing averages from two different populations, well, that tells me I'm going to be doing a two-sample t-test. Again, two populations. I'm comparing them. Excuse me. So I'm comparing these two populations, and I'm comparing the averages of them, so that's going to give me a two-sample t-test. So we are going to go through here, and we're going to run through... Well, first of all, let's do our null and our alternate. For our null hypothesis, we assume that the average of the CPMP is going to be equal to the average of the traditional. Remember, null is dull. You can also write it out like this. If there isn't a difference when you subtract the two averages, you should be getting 0. So those are your two options if you want to write your null hypothesis. For your alternate, now, we're not specifically trying to see if one is greater or less than the other. We're just looking to see if there's a difference. So what that would look like is the average of C is not going to be equal to the average of T. They're going to be different. That's what we're looking at here. Not necessarily greater or less, just a difference. So what we'd also be looking at here is if we subtracted them, we wouldn't get an answer of 0. If the CPMP student scored better, then when you subtract those, the average scores, you'll be getting one greater than 0. If the CPMP students did worse, then you'd be getting average less than 0. So all we're really concerned with here is that it doesn't equal 0, that there is a difference. We don't necessarily care who scored higher. We just want to see if there's a difference. So those are our null and our alternate hypotheses to start out. Next, we want to check our conditions. So let's see. Let's check what's going on here. It's an innovative approach, group investigations over a 3-year period. Okay, because one thing I want to check here is whether they imposed a treatment. They did. The treatment that was imposed was students either did the CPMP or they did the traditional math program. Since this is an experiment, we can approach our conditions a little bit differently. 10%, we don't necessarily have to account for that since it is an experiment. So we don't necessarily have to do that. However, there are a few other things we want to look for. We want to look for random assignment. Did they do that here? And students had solved scores from students. Okay, well, there was no random assignment, but again, it's an experiment, so we'll assume that in the course of this experiment that there was some random assignment going on. However, we want to make sure that we have our large sample / our normal. That's important. In this case, we want to see if both sample sizes are greater than or equal to 30. 312 is definitely greater than or equal to 30, as is 265. So we've met that condition. Again, since this is an experiment, you don't have to meet the 10% random. You want random assignment. They don't mention that here, but we will, let's see, I'm even double checking. Yeah, I'm not really seeing random assignment, but we'll assume that since it's a well-done experiment, that should be happening. All right, so since we've got all the stuff here, we've got all the information we need, really, I'm going to pull up the calculator, and we're going to calculate this out. Pull it up, all right. We're going to jump to stat here. We're going to go to tests, and we're going to be doing a two-sample t-test right here. All right, we're going to be entering in the statistics, which they give us here. I have to start at the bottom here for some reason. It's a glitch. I'm going to enter in 29. It's my... Nope, it's not. My mean isn't 29. My standard deviation is... I got to check this out. 18.8. My first one. The average was 29. Sample size was 312. For my second, my sample size was 265. My mean was 38.4. 38.4. Whoops. Always double check to make sure you're entering the right numbers. And then for our standard deviation, 16.2. All right, and now let's see what we're trying to prove here. We're just trying to prove that they aren't equal, not necessarily that one's greater than or less than the other. We don't want to pool our data. We don't do that in here. Then we hit calculate, see what we get. Oh, wow. Now take a look. We get a p-value that says 2.37, and immediately some people will be like, oh, that's greater than 0.05. But remember, your p-values can't be greater than 1. If you're seeing something greater than 1, go at the end here. You'll notice I have e to the negative 10th power, which means this is in scientific notation. I'm getting a very low p-value out of this. So I'm going to write down my critical values, the things I need here. I'm going to write down my test statistic, which was negative 6.45 standard deviations. That's pretty high. P-value, for all intents and purposes, actually I'll write it in scientific notation, 2.36. I was tempted to just write 0 because it's really close to 0, but we'll go with the scientific notation here. Again, if you see a value that is greater than 1, or even is 1, chances are it's in scientific notation. Be mindful of that. That's really low. And remember, our significance level, we usually keep it at 0.05 unless they tell us otherwise. All right, so got this out of the way. We get the calculator out so I can write this. Good. So I got really low p-value. Since, whoops. I'm going to just abbreviate this. P-value less than significance level, reject the we reject the null. What does that tell us? We have evidence. There is a difference in scores between CPMP and traditional students. Well, that's my cat, if you can hear her in the background. All right, so now last thing, we want to establish what kind of error could have occurred. This is becoming pretty common in these problems. Remember, reject the null when the null is true. That's type 1 and not type 2. If it was a type 2, that would mean that we failed to reject our null hypothesis, and the error could be that we're failing to reject it when we should be. In this case, we did reject the null, which means we could be rejecting the null when we shouldn't be. So that would be a type 1 error.